Hello? 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 Okay, great, it works. Okay, good morning everyone. Welcome back. Hopefully everyone enjoyed a great fall break. So now it's getting colder, right? And it's later to guys sunshine, yeah. So yeah, it's a little bit dark outside. But anyway, we have a lot of students coming to the lecture. So first of all, I'd like to mention that maybe you have noticed that we have extended the deadline for homework 2 and midterm project report because quite a few students are requesting for that. But I did say quite a few submissions have been made. So thanks for your hard work. So to be fair to those who, are able to commit to the original deadline, you receive the actual bonus credits if you submit it. But for who, due to various reasons, feel like I would need a few more days to finish homework 2 or the midterm project report, please take your time and let's submit it in time. Okay? And again, we highly encourage you to leverage office hours. We have office hour every weekday, but according to our experience, most office hours are just empty. I don't know why. Because if you want to get to the greatest help, it's best to come to the office hours and have a face-to-face chat. And every weekday we have plenty of office hours. Although we do watch the campus forum. We want to respond to your questions as fast as we can. But our TMs they have their own classes, their own schedules, meetings, so they're all very busy. So they cannot you raise a question last minute and I respond to you this minute. It's actually infeasible, right? So they try to do that, but it's not. It's quite hard. So again, if you want to fully leverage the advantage of these office hours, please come to the office hours in person. That will give the best help. And also, we have released homework 3 today. These are about perception. Compared with the workload in homework 2, even homework 1, it is much lighter. So we won't be able to make extra deadlines for homework 3. So 2 weeks are far more than sufficient. So, but again, don't try to finish it like 1 hour before the deadline. You won't be able to make it. If you can do it right now, I'm guaranteed you will be very comfortable with that. Okay? Yeah, so, and the second thing I want to mention about the midterm feedback that was made by the lecture right before the fall break, and we have gone through in every detail of your feedback. It's really helpful. I appreciate your comments and many useful. So here I just want to clarify a few points which are covered by you and also give our plan. So someone mentioned that they would like more examples for homework and practical applications. This is what we did. We tried to give as many examples for homework as possible, but the homework problems are designed not as a straightforward extension of the examples covered in the class. It's not just like I modify some numbers and I let you redo it. That won't help you understand basic concepts. It will make a little bit change on that, And this is just to deepen understanding. Not you could just, okay, I just copy the solutions, copy those formulas we show in the lectures and change the numbers. That won't be like that. But other than that, I mean, just a little bit of change. As long as you really understand the concept, so don't worry about that. You will be fine. And some examples of practical applications. That's a very good suggestion. We will introduce more examples of practical applications before we talk about every detailed algorithm. So in case that someone might feel, okay, what I'm learning is outdated. Actually, it's not. So don't be misled by the news or whatever hype messages. Yeah, a lot of applications are done by artificial neural nets right now, like face recognition, voice recognition, even some automated driving system. Deep neural networks are kind of like critical component, but there are a lot more applications which are not dependent on deep neural nets, like support vector machines, well, logistic regressions. They're used everywhere. Right, so we're going to give some examples. I'll talk about the examples to give you a sense. They're actually very, very common, but it's not as because easy. It's not as challenging as you think. Okay. And third complaint is about writing with LaTeX is hard. Well, honestly, I mean, all the in all areas of technology and science, LaTeX has got common language. No one is going to use Word to do that. That's why we request everyone to get used to LaTeX, and we provided the template. If you notice that, I mean, every release, the homework, there's a company template called EMAC common.tax, right? I stole from my advisor, and my advisor stole from MIT. It's very good, very convenient piece of macros defined, so that we use that macros to write the mathematical symbols. It's very convenient and very useful. So we provide all the templates, and so that actually you don't need to. What you need to do is just write down the solutions with LaTeX. So and also we highly suggest you to use Overleaf. That means you even do not need to install any LaTeX editing environment, right? You just write it on your browser. It's very, very convenient. But if you still feel like doing this is really hard, it's really you're really sick of this, and you insist on that Word is your true love, and you want to use that instead, you can come to me, and we can discuss. Okay. But still, I highly suggest you to use LaTeX, because you're going to use them as long as you're working in science and technology areas. Okay. But we provide alternative choice if you still stick to Word. Okay. And okay. Not interested in proof-based questions. That's good. I've seen many of you are very passionate about programming portions of the assignments. That's really good, because this class, as we emphasized at the beginning, stressed on practice. Right? So this is not a theory class. We're not gonna go through many detailed proofs. The only theories we have to cover is because without them, you don't know why those algorithms were invented or developed. That's all. So actually, maybe there's a misunderstanding here. Because actually, we really don't have any specific proof of these questions. If we refer to some theories, we just want you to understand that theories. We don't want you to, okay, based on these theories, please prove me a new set of lemmas or corollaries. No, that's not what we seek for. So we just ask you to be able to understand what those proofs, what those theorems are saying, right? And why those theorems motivate the invention of algorithms like support vector machines or perceptrons, all those kind of stuff. So there won't be any proofs in homework assignments, and and in a final exam. So don't worry about that. And finally, heavy workload. Well, this is something I have to clarify because we emphasize this beginning. This class is not easy class, right? So this is also feedback from previous students. Most of them are enjoying this heavy workload because at the end of the semester, they feel like they really learned something. They really feel like confident about this machine learning area. So that's why we have to maintain the certain amount of workload to ensure everyone is well trained. But if you feel like, oh, this is too heavy and I cannot afford that, and please come to the office hour. We can have a discussion. Okay, and we're quite generous about the grade. But the prerequisite is that you must finish those, right? You cannot give me an empty submission and saying, can you give me like 60 points or 100 points? That won't be possible. But as long as you do that, we're quite generous about the points. Okay, but and also as you said, if many of you like requesting extension because of various reasons, we're trying to satisfy your request. We're trying to account for your request because we know everyone is multitaskers, right? Everyone is busy. So that actually implies that your target function must be inside the hypothesis as well. Otherwise, you can always find a data set which can differentiate your target function and any hypothesis in the hypothesis space, right? So this is called agnostic learning. Why? Because we are agnostic about where the target function stays in, right? So the critical difference or the critical point we should be aware of agnostic learning is that because the target function is no longer necessarily stay inside the hypothesis space. That means your training error is not guaranteed to be 0. Okay? So that's the key difference from consistent learning. So, but our training objective is still there. We still want to minimize the training error. Right? We want to make the training error to be as small as possible, so that we expect our true error, in other words, the generalization error, to be as small as possible as well. Okay? That's the strategy for the agnostic learning. Right? So the computational learning theory, like the goal of the computational learning theory about agnostic learning is that, okay, so if I can get a training error, right, how can I derive some kind of bound or description about the generalization error based on the training error? In other words, can I use the training error to estimate some bound for the generalization error or the true error? Right? And how do we do that? Right? The important tools we're going to use is called tail bounds. Right? Tail bounds basically just describing the chance that the random variables deviates from its mean. Right? So we know that from statistical classes, we know that most likely the random variables will stay around the mean, right? Around its mean. Right? If your random variable wants to get quite far away from its mean, the chance is pretty low. Right? And intuitively, the far away your random variable takes a value from its mean, the lower the chance. Right? So tail bounds are used to characterize the bounds for such kind of chances. We introduced several commonly used bounding inequalities like Markov inequality, Chebyshev inequality, and so on. Right? So the Chebyshev inequality is saying that, okay, for any random variable, the probability the random variable take a value k standard deviation away from its mean this probability is less than or equal to 1 over p squared. Right? So from this inequality, you can say the larger the k, the smaller the probability. It actually implies that, okay, if you want to take some value very far away from mean, the chance is very, very low. Right? But the most important inequality we're going to use is called Hopkins inequality. Okay? So Hopkins inequality upper bounds how much the average of a set of random variables differs from its expected value. So it's talking about the average of a set of IID random variables. So suppose I have m random variables, x1, x2 to xm, right? IID means that they are independently distributed. Right? They're not related to each other, but they follow the same distribution. And of course, because they are IID, the expectation of each random variable is the same. We can denote it by p, right? And at the same time, we average of these m random variables. So we can sum over x1 to xm and divide it by m, right? So this is called p bar. P bar is essentially an empirical estimate of the expectation, right? So just like imagine you're doing a Torsian experiment of horns, right? So you want to estimate the chance you see the heads. Right? How can I do that? I know that internally you gotta have chance, right? Which is expectation. But you want to estimate this chance, how do you do that? You just toss the coin like for 10 times or 100 times, right? You just calculate how often the heads are out, right? And just calculate the ratio of the heads over the total number of the torses, right? So this is the average, right? Because each core tossing, the outcome you can view is a binary random variable, right? If you have a heads up, the random variable takes value 1. Otherwise, it takes value 0, right? And the ratio of the heads up is actually the average of these random variables, right? But the expectation of the heads up is essentially the probability that indicator or binary random variable takes 1, right? So you can see that p bar, the average of these random variables, is an empirical estimate of the true expectation or true mean. Right? So this one, just be careful. This one is still a random variable. Why? Why this is still a random variable? P bar.
Because it's just the sum of a bunch of other random variables?
Yes, exactly, right? So remember, p bar is a summation over a set of other random variables. In other words, it's a function of random variables, right? So the function of random variable is another random variable. So p bar is kind of, we can view as a random estimate of some ground truth quantity, which is the mean of each random variable. Right? So now we have these preconditions. According to Hopkins inequality, we claim that